Watch this video as I show you exactly how to simulate crack growth using XFEM in Abaqus. First, we'll start with a simple 2D crack growth example. Then we move into a full 3D XFEM model and finally wrap it up with a realistic 3-point bending crack growth simulation. By the end, you'll not only understand the workflow but also know how to apply XFEM confidently to your own projects. So let's get started. XFEM in Abaqus is a game changer for crack growth simulation, but only if you set it up correctly. Get it wrong and you'll be greeted with everyone's favorite message: too many attempts, error. But why does this happen? And why do so many people struggle with XFEM? Because a few crucial settings decide whether your crack will grow as expected or if your simulation will completely break down. Today, I'll guide you step by step through the right way to set up XFEM in Abaqus so you get accurate, reliable results without Abaqus throwing a fit. Let's get started. First, let's define the geometry. The geometry includes the plate and the crack itself. So let's create the plate first. Name it plate. It should be 2D planar, deformable, and let's put this value on 400. We create a simple rectangle just like this. This should be 200 and this must be 100. Enter, scroll button, done, and we have the plate. Now let's create the crack. So from 2D, you would put this on wire and we create just a simple line. We assume the crack to be 20 millimeters. Then we have the crack. Now that we have the geometry, let's move to defining materials properties. Materials properties in XFEM is pretty crucial, so watch this section carefully. So I would like to start with the general density and it should be 1.19 E-9, which is for a polymer, but you can stick to this video even if you're working with the steel. So from the mechanical elasticity and elastic, I would like to have 3240 and 0.35. From mechanical damage for traction separation load, I would like to have maximum principal stress damage. It's best for brittle materials like polymer and composites. By adding this, we assume if this stress is higher than the critical stress, the crack would initiate. So I put the value of 100 here. And I'd like to have a damage evolution in the sub option, and instead of displacement I would like to have energy. This energy is 0.7. so by defining this one, instead of the material failing instantly, it gradually reduces the stiffness, so we will have an accurate damage growth behavior. Everything is set. It's time to create the section. I'd like to put it on the plate. So from here, create section. The section must be solid homogeneous even though we're working with a shell plate. If you wonder why, using a solid homogeneous section in this case ensure that the mechanical properties of the material are uniform throughout the plate, enabling accurate representation of how stress concentrate around the crack under uniaxial tensile loading. In other words, it simplifies the setup without compromising the fidelity of the stress analysis. So this section must be solid homogeneous. The material is material 1 and we assign this to plate and we uncheck this one because we don't want to have too many sets. Done and OK. If you want me to do the same thing for the steels or ductile materials, just let me know in the comments below. The property section is completed and now it's time to assemble the model. So from here I create the instance. First I create the plate and OK. Now let's translate this. We can select this one to put it just right here and OK. Then auto fit the view. Now create the crack. We want to translate the crack as well. So done. We can simply put it here and OK. Now it's time to go to the step. So we want to create this step. It should be static general. We need to toggle this on because we have large displacement around the crack. This must be 100,000, 0.01, 1e minus 9 and 0.1. Then okay, the step is not over yet. We need to go to the field output, and here we need to toggle a couple of things on. First, we need to go to the state. We scroll down, we should check load XFEM and status XFEM. Then we can close this, and in the failure and fracture we scroll all the way down and we check this two guys. And okay, now it is done. We're good to go to the interaction. Here's one of the most important part of this simulation. So let's go to the spatial, and from crack we go to manager and create. This crack must be XFEM. First, it asks us to select the crack domain, which is the plate, and we need to check the crack location. So we check this one and we click on this cursor. Then we need to select the crack, and done. So the crack location is created and we set the region. Now it's done. You should see all these green X's all over the material. If you don't see that, something is wrong. Now let's create the final thing here, interaction. From the step initial, we need to select XFEM crack growth in order to allow the crack growth in the setup. And okay, now it's time to go to the load to define the boundary conditions and the loading. So first we need to create the boundary condition. I would like to put it on manager, create mechanical symmetry, continue, and we need to select this one, done, and in cast. It cannot move and it's fixed, and we want to create another one, which is the displacement rotation, and I select this one. We should fix it in the X and the rotation in the initial step, but in the step 2 we can have the displacement of 2 mm, so it only can move in the Y direction. So this is over. Many people struggle with the boundary condition and they don't know what values they put here or what sort of boundary condition they should use. And if that's you, comment down below to let me know. I will help you. Now let's focus on meshing, which ensure the accuracy of the model. Meshing is the last step before submitting the job, so bear on with me. We go to the part, and here I would like to put this value on 4. Then we mesh the model. This is a good mesh. The finer the mesh, the higher the accuracy of your model will be. You can go to the job. This is the moment of truth. And if we set everything correctly, we should have a realistic crack growth. Let's submit the job and find out. We say okay, and it gives you the following part have some element without assigned. This is the wire. We don't need the section assignment for this one. So we check yes. This is just a warning, it's not an error. Before jumping into the results, I like to ask you a quick favor. If you're enjoying this video, let me know in the comments. Your feedback helps me improve and create better Abaqus tutorial for you. Now let's go to the results. We click on this one. And yep, we see a crack opening here and grew through the material, and we can see the animation here, but I want to put it on slow. We can have the animation just right over here. We see a crack initiates and we have an opening here. If you have more displacement on the top, you would see the crack can zip through the thickness, and we have two separated surfaces. Alright, I'd like to put this on the last increment, and other things we can have FILSM, and I like to talk about this a little. So what is FILSM? This is represent the sign distance function for the level set method used in XFEM. It defines how far a point is from the crack surface. Positive values indicate material away from the crack, while negative values indicate material inside the crack. When this is 0, it defines the actual crack surface. When it's greater than 0, the material that is intact and not cracked, while it's lower than 0, the material inside the crack fully separated. Zoom in a little and you can see and compare. The next thing we can see is PSILSM. So what is this one? This stands for Principal Level Set Distance Field. It used to track the crack propagation direction in XFEM simulation. When this value is 0, it defines the crack surface and it determines the principal direction of the crack front, which is right over here. Next thing we can do is to see the displacement, and as you see, the displacement is the highest here, or we can have the option and comment, and from feature edges we can remove the meshes and we can see the crack even better. And here, if we want to exaggerate it a little, we can put the value of 10 for instance here, and we see the crack is in an exaggerated way. Let's see the stress, and here is the stress and the crack front. Thanks for watching so far. If you are enjoying this tutorial, don't forget to drop a like, or if you have any question, just ask me in the comments down below. I respond to every single one. Thank you. By the end of this video, you'll know exactly how to simulate 3D crack growth in Abaqus using XFEM method. We'll walk through the setup, step-by-step, geometry, mesh, damage setting, and critical options that make or break a successful crack simulation. Whether you failed before or you're trying this for the first time, this guide will get your crack growing reliably. And if you want to download the simulation files, just check out the pinned comment down below. Let's get started. Okay, as always, we start with a part, create a part, name it plate, because we're going to have two parts, and it should be 3D deformable solid extrusion. Make this 400, continue. We need to create a rectangle just like this. This guy must be 100, and this one must be 200. Scroll button, done, and the depth can be 3. Okay, this is the plate we have. Now we're going to create the crack. So we name it crack 3D deformable shell extrusion. Continue. We just create a line just like this, scroll button, and this should be 40 millimeters. So the crack we have is 40 millimeters, and the depth is 3 millimeters, the same. And here we have the parts. Now let's go to the property. In order to download the properties, let's go to the feamaster.com. Okay, this is the feamaster.com. Go to the shop and material property packs. Here we have aluminum XFEM, add it to the cart. It's a free download as you see. And then go to the checkout. After filling everything, you're able to download this file. And I'm opening it. Okay, this is the file we have. We can copy and paste everything. Let's jump back to Abaqus, create the materials properties. This is aluminum. We need Young's modulus, so let's create the mechanical elasticity and elastic. Copy this one and paste it here. Then we need to have mechanical plasticity and plastic, because it is aluminum, as we have the plasticity at the tip of the crack. So let's go here and copy and paste this values here. Then from mechanical, damage for traction separation loss, max PS damage, you need to put the maximum here. This is here 350, and we need to have damage evolution. Put this one on energy and copy this value, paste it here, and okay, and we're done with the properties. Now we need to create a section, solid, homogeneous, and continue. The material is aluminum, and we need to assign the section. We assign the section here, we uncheck this one, and done. Okay, as it turns green, it means the material is assigned. Okay, let's go to assembly. We assemble the model here. Let's put it on independent, select both, and okay. Now I want to translate this one from here to here, basically. Yep. And we need to move this one, so I select this one, put it this one here to here, and as you see we have the crack. The difference between this video and the previous one is that we should have the 3D crack. We cannot just have a wire or just a line, we should have a plate, or sometimes we have semicircular cracks or round cracks. Okay, we're done with the assembly. Let's go to the step, create a step. Step 1, initial static general, continue, toggle on analgium, and here we should have like 1 million, 1e minus 2, 1e minus 9, oops, 1e minus 9 here, yeah, and 1 is okay here. Now we need to go to the field output manager. Here I need to go to the failure and fracture and go all the way down, toggle these two, and from state we should go to the STATUSXFEM and toggle this on and OK in order to see the opening of the crack or the separation of the material. Now this is the step. Let's go to the interaction. Here we need to go to the special, and from crack let's go to the create. Now select XFEM, continue, and you need to select the crack domain first. This is the crack domain or crack region, and we want to define the crack location. So select this one, edit, and maybe it's better to rotate to select the crack, and this is the crack, and done. As you see it should turn magenta, and this is the crack, and the other part is the crack domain. And okay, now you would see all these X's, it means it is assigned. Now we need to create one other interaction. From step initial, XFEM crack growth, continue, and we need to select the crack one, and okay, in this manner we allow the crack to grow. And this is the interaction. Let's go to the load. From the boundary condition manager we create the boundary conditions. First I need to create the symmetry or encaster. Select everywhere, then hold Control and deselect others. We only need the bottom part, and done. It should be in cast and done. Next we need to create another one from the displacement and rotation type. Now we need to select this part and hold Control and deselect the other part, and as you see we only selected the top part, and done. It only can displace in the Y direction, so I leave it open and select others, and okay, and it should be propagated. And that is for the boundary condition. Now we need to create load. So from here, create load. Step 1 should be pressure. Continue. We rotate it a little, select this top part, and done. And it should be uniform. And as this is pressure, we want to have the tension, so I put a minus sign here, and done. Here you see the arrows should face upward. And yeah, that's pretty much everything in the load. Let's go to the mesh. Let's make the mesh dependent. So from here, simply select these two and select make dependent. I made a mistake, sorry. And here we should go to the part, and this is the plate, and put this seed on 4, then okay, then this one, select yes. Now it's good, we don't need to mesh this part. So in the assembly it should look like this. Now we're good to go to the job. But before creating the job, I want to ask you a favor. If you enjoyed this video so far, please leave a comment for me down below. It's totally free for you, but it motivates me to create more videos like this. Thank you. Now create the job, name it XFEM Crack Growth 3D. That's a long name, but it's okay. Continue. Okay. Now we need to submit the job, and it says some parts haven't assigned the sections, but that's okay. Click on yes and see how it goes. Now the job is running. Let's go to the monitor, and as you see, we don't have errors and the warnings are fine, and the job is running as you see. Alright, now it's finished. As you see, it says completed. Let's go and take a look at the results. I put it on this. Let's switch the view, and as you see, we have a crack growth here. Let's put this one on option, common, and from here we can have feature edges, and put this one on OK. And you see here the crack growth, and it is more visible in this view. We can have different options. For instance, let's see the animation first. I want to make it slow. The crack grew, yeah. Okay, this is the animation. And let's go see other things. Phi LSM. Let me reset the view. I put it here and make sure to put this one like the very final step. So I want to talk about what Phi LSM is. This is represent the sign distance function for the level set method used in XFEM. It defines how far a point is from the crack surface. Positive values indicate material away from the crack, while negative values indicate material inside the crack. When this is 0, it defines the actual crack surface. When it's greater than 0, the material that is intact and not cracked, while it's lower than 0, the material inside the crack fully separated. As you see here, we have the value of 1e minus 6, and as we go forward, it would be 0.85, and the region is here. Let's go for the next one, Psi LSM, and I want to talk about this one also. So what is this one? This stands for Principal Level Set Distance Field. It used to track the crack propagation direction in XFEM simulation. When this value is 0, it defines the crack surface and it determines the principal direction of the crack front. Let's see how it is in the beginning. As you see, we only have it here, and the value of 0 is here, and as we go forward it propagates, and this is the 0 here. And other things we can see here is the displacement. This is the amount of displacement, and STATUSXFEM, we chose the enriched elements. 1 means fully cracked and 0 means uncracked. So if we put this one, comment on exterior edges, just like this, and if we zoom in, you see here, we only have this one, then it opens up, and as you see here, we have values just close to 1. It means the crack is propagating. Thanks for watching so far. If you are enjoying this tutorial, don't forget to drop a like, or if you have any question, just ask me in the comments down below. I respond to every single one. Thank you. In this tutorial, we're simulating crack growth in a 3-point bending test using XFEM in Abaqus. You'll learn how to model geometry, define material properties with fracture behavior, set up XFEM crack initiation and propagation, and analyze how the crack evolves under bending load. We'll cover everything step by step, from part creation to meshing, boundary conditions, and post-processing with fields like STATUSXFEM, PSI-LSM, or Phi-LSM. So let's get started. Okay, let's start with creating the part. Create part. We name it beam 3D deformable solid extrusion and continue. We want to create a simple beam just like this, a rectangle. Then we add the dimensions. The length must be 80 millimeters, and this one should be 4, and scroll button, this one, which is the width, must be 8. So we have the beam. Now it's time to create the support or span. I would call that the span. It should be 3D, discrete rigid, solid extrusion, and continue. Now we create something like this. This should be 8, and this one must be 4, scroll button once more, and this one should be 8 as well. Now this is the span or support. Then we need to create the crack. The crack must be 3D deformable shell extrusion and continue. We just want to create a simple line just like this. This should be 1 millimeter. 1 is enough. Okay, same as previous one. The depth should be 8. Now we have all the parts, crack, span, and the beam. Now it's time to go to create the materials properties. We create the material properties, general density. The mass must be 7.8 E-9. Then we go to the mechanical, elasticity and elastic, 210,000 and 0.3. This is for the elastic. Now we should go to mechanical, damage for traction, separation loss, and max PS damage. Let's put the value of 120 megapascal. Don't mind this if you're not using the 2024 version. And we need to go for damage evolution. Put this one on energy, and the mode should be power low, and 40,000 joules. We copy that and paste it here. Also make sure to put the power on 1 here, and okay, now we need to create the damage stabilization cohesive 1E minus 5, and we have everything: density, elastic, max PS, damage evolution, and damage stabilization cohesive. And okay, now we need to create a section. Must be solid, homogeneous, and continue. Okay, and we select this one. Then we assign the section to this one. Just uncheck this one and okay, and done. We don't need to create sections or assign materials properties to span or the crack. And okay, let's go to the assembly. We would have an error here if we want to have the span alongside the crack and other things. As you see here, it says a solid rigid part cannot be instanced for the assembly. Now to fix that, we go back to part once more, and we need to go to the span, left click and hold on this one, and go to the create shell from solid. We select this one and done. And as you see, now if I cut this, it is hollow. Before that it was a bulk, but now it is hollow. Now we can create that in the assembly. Another thing that we can do here is also to create a reference point. So I would like to create a reference point right here. So in that case, we don't need to create an interaction of rigid body to call this a rigid body. So this is the discrete rigid and can be used directly. Okay, let's go to the assembly. Now as you see, if I select everything here and click on OK, I can create them. Alright, now it's time to translate them. First this one, scroll button here, can go here, and that's it. Now I need to translate this one, select and this reference point can go here. Now I need to create more of this, so by here span, I click and apply, then I want to do that once more, just like this. Then here, scroll button, reference point, then you can select this one and put it here, a simple translation, and this one the same thing, here can go to here. Now we have our assembly. The assembly is done. Now we can go to the step. Now we want to create a step. Step 1, initial, static, general. Then we can go here, 1000, 3 more zeros, should be 1 million. This can be 0.1, 1e minus 9, and 1 as the maximum is okay. Then okay. Now we're not done with it yet. Let's go to the field output manager, and here from status you should toggle this one on, status, in order to see the separation. Plus we need to go to the failure and fracture. You go all the way down and phi LSM and psi LSM, check them on, and okay. Now we're done with the step. Let's go to the interaction. We need to create an interaction property. It should be contact, continue, mechanical, tangential behavior, and we would like to have a penalty 0.15, and from mechanical normal behavior we would like to have a hard contact. And okay, now we need to create interactions. From this one, step 1, surface to surface contact, but in this mode we're going to select the surfaces manually. I don't want to do that, so there's an easier option to do, is to go to find contact pairs. If I click on this one and find contact pairs and select them here, you see it shows the contacts, and if I click on OK, and the interactions are created. As you see here, we have one contact between these two, and we have one contact between these two, and there's another one here. So we do have the contacts, and it made our life easier. Now I need to create one another interaction from special, and in the crack create, select XFEM and continue. We select the crack domain, then we toggle this one on, crack location, and we zoom in here and select the crack and OK. Then OK here. Now we need to create another interaction here in the step initial, XFEM crack growth, and this should be crack 1 and OK. And as you see here, we selected this crack to grow. Okay, this is done. As far as I'm concerned, there's no interaction to be created. Now let's go to the load and boundary conditions. Okay, this is easy. We create the boundary condition from here. I hit create. We can create one from the encast mode. Continue, we select this one, we hold shift and select this one, these two reference points, and done, encast, and OK. Now we need to create another one from the displacement and rotation. Continue, I select this one, and done. Let's check all of them here for the initial step. Now in the step 1 we can modify that, so I'd like to put the value of -8, and okay, it means this span would displace 8 millimeters to opposite of Y direction. And this is the load and boundary condition, and we're good to go to the mesh. Now we need to select part, this one. First we need to assign mesh control. We select this and done. Let's put this one on quad and structured. Okay, then we need to seed the part. 0.8 is okay, and yes, now this one is meshed. We can go to the beam here. We need to select this one, the same number, 0.8, and okay, let's create it. Yes, and now if we go to the assembly, you see as we selected the same global seed size, these nodes are attached together. So here is fine, and here are in the same line. We check this one is also in the same line, and here also the lines are in the same one. If you see a mismatch between the two, it means the numbers are not correct and needs to be corrected. Okay, the mesh is also done. Let's go to the job, but before going to the job, I want to ask you a favor. If you enjoyed this video so far, please drop a comment down below. It's totally free for you, but it helps me grow faster and motivates me to create more videos like this for you. Okay, let's create a job. Here we create a job, we can name it 3-point bending XFEM and continue. Okay, then submit the job. It says the following part doesn't have any sections assigned, is okay, and you submit the job. Okay, let's take a look at the results quickly while the job is being run. And yeah, I think that's enough for now. We can terminate the job. From here I click on kill. Yes, the job is terminated. It probably be aborted later due to the very coarse mesh we have here or the high displacement, but it's totally fine because this video has the educational purposes. It's up to you to modify it for your model. Alright, let's take a look at the animation. Just like this, as you say, it goes down and the crack grew. Let's stop it here. From option, comment, we can go to the free edges and we can see the crack growth better. And from here, I would like to put it on this one to see that in a slow motion pace. Put it here, then from the side view, and there we go. Here the crack is propagating all the way to the top. Yep, and we can also see other things here like phi LSM or psi LSM. I already explained them in the previous video, what they are and what do they mean. Please check the video. I put the link on top right here, and this is the contour of phi LSM. Let's go to the very end, and we have the contour of psi LSM in here. As you see, the crack propagates. Now that you've successfully learned XFEM in Abaqus, it's time to take the next step, fracture mechanics simulations. Click on the video on screen and I'll see you there.